Okay, so this video, we're gonna go through section 3.8, which is choosing the best model. So in the previous couple sections, they talked about the different types of models that we'll see in scatterplot data. The first one was linear. And so linear model based on that least squares regression line was kind of the big idea of this whole unit. And so we talked about how we can linearize data so that that linear model will work. So one way that I know that data is linear is that if I look at the equations or the residuals or the computer output and there's no log or ln on any of the variables, so they're all just the variables, in this case area and age, not log of area or log of age or ln of area, ln of age, that tells us that we're looking at a linear model. To know whether a linear model is a good fit, we want to look at essentially two different things. The first thing is the plot of the residuals. So if I look at the residuals, notice that there is no curved pattern. Essentially, you want to think about it as though the points are all over the place. So if I were to connect them, I would just have this kind of zigzag of connections with the points. And that's something that tells me that I have an appropriate model. Okay, so that's one way that I can tell my model is appropriate. So I know it's a linear model because there's no log or ln, and then I know that my model is appropriate because of this graph of residuals. I can't, you know, if I were to connect these points, I would just have this big like zigzag pattern. There's no curve that would connect them. So using a model, you will have problems that will ask you to estimate some answers. So this one didn't give us computer output. It actually gave us the least squares regression line. So if I start with that line, so if I know that area hat is equal to 0.439 times the age plus 6.226, I can estimate the area for a 75-year-old tree by just plugging that value in. And so since it's already equal to area, that tells me that area hat is equal to 39.151. This problem did give me units for the response variable, so I'm just going to write units. Remember, because it's area, it should be square units. And again, simply just because they didn't give us those values, so I'm just going to generically say it's square units. So I'm plugging the age into my least squares regression line to predict a value or estimate a value like that. The next type of function that we looked at was exponential functions. So exponential functions, I can tell, are used when I have a log or an ln of only the response variable. Remember that when it's written like this, it's always the response versus the explanatory. So it's always y compared to x. So then the graph here is giving us a graph of residuals. Again, there is no curved line, right, that I can use to connect these points. I get this weird zigzag. The points are essentially all over the place if I were to try to connect them. Okay, so that tells me that an exponential graph relationship is a good fit. So it's an appropriate model. Because there is no curved pattern. Another way that I can tell that a model is appropriate is by looking at the computer output. So this problem also gives me computer output. Remember that the r² value is going to tell me whether something is an appropriate model. And so this percentage tells me that my model is appropriate. Again, because it's close to 1 or 100%, since that's written as a percentage, right? 99.45 is very close to 100%. So that's telling me that I have a good model in that exponential data because I have the log of just my response variable. So this question is asking me the same thing. I'm going to estimate a dosage given a weight, but first I have to write the regression line. So remember that the regression line is going to be our response variable hat. So our response variable is log of dosage. So log, and I'm just going to write dose for it to be concise. So the log of the dose hat is equal to, remember this is your A and this is your B, so it's your y-intercept 2.25572 plus 0.001404 times your response variable is weight, so times weight, is the linear regression line. Okay, so I'm going to use that linear regression line now to estimate the dosage given a weight of 153. Again, I didn't have units here, so I just left them off. Normally it would match whatever is given in the problem. Okay, so we're going to take our regression equation, log of the dose hat is equal to 2.25572 plus 0.001404 times the weight, which we're looking at a weight of 153, I'm guessing pounds. So that means that log of a dose hat is equal to, so if I calculate this value in my calculator, I get 2.470532. What's different here is that that's not my answer because I don't have the dosage by itself, right? I want just the dosage. And so remember that whichever kind of log you have tells you how you exponentiate. So if it's a regular common log, you're doing 10 to the power. If it's a natural log, you're doing e to the power of the equation. Okay, so since this is a common log, we're going to raise everything to the 10th power. Sorry, we're going to exponentiate everything with a base of 10 so that the log will cancel. So this means that the dosage hat, so our predicted value, is equal to 10 to the 2.470532 power, which gives us, and I'm just going to do a couple decimal places here, 295.48. And again, I don't know the units, so I'm just going to write units. Okay, so because that was a common log, I used a base of 10 to exponentiate the equation. Remember in the previous one, I used ln examples, so we used e because of the type of log that we were given. The final type of equation is a power equation, when I got kind of close there. So a power equation, if I can bring this down. The power equation I can tell based on looking at the fact that both variables have a log or an ln around them. So I know this is a power function, or I'm checking this on a power model because I have log of age versus log of the diameter. So both my response variable age and my explanatory variable diameter have a log in order to try to linearize the data. So looking at the pattern, I have an appropriate model. Again, because there is no curved pattern, meaning I cannot connect my points with a nice, whoa, I skipped a bunch, with a nice curved line, right? I've got this crazy zigzag thing going on. Okay, so that's not a beautiful curved line. So that means that this model is appropriate to be a power model. Similarly, I can look at that R squared value. This is a high percentage, close to 100%. Okay, so I want to be close to 100%. Anything in the 90s will always be good. Okay, so I know now that I have a power model, and I can tell that based on the fact that I have log of both variables. So then to create my least squares regression line, remember that I'm doing, my response variable is log of the diameter. So when I write my equation, I'm looking for log of diameter, and I'm just gonna abbreviate hat, is equal to, remember that this is my y-intercept, the constant, negative 0.330, plus my slope, 0.9548, times oops, I looked at diameter, sorry, that was the response variable. I was looking up here in the wrong spot. That's my x. Sorry, times log of diameter. The second one's your x, right? So this would be my x value, this would be my y value. So it's log, sorry, I did that fast. So it's log of age is my y, log of diameter is my x. Okay, so I'm taking log of age is equal to negative 0.330 plus 0.9548 times the log of the diameter. And then I'm given a diameter of 1.75. So I'm going to plug that into there in order to estimate the age that they're looking for. So log of age, hat, is going to be equal to, I'm going to be lazy and drop some zeros, so 0.33 plus 0.9548 times the log of 1.75. Okay, so when I'm calculating this, I'm calculating the right-hand side, so it's all numbers and a function. And so negative 0.33 plus 0.9548 times the log of 1.75 gives me that the log of the predicted age is equal to negative 0.979. Okay, so again, if I have a scientific calculator, if I'm working on Desmos, I'm just typing that straight in as I see it. If your calculator kind of works backwards, I would suggest just pulling up Desmos and typing it in so that you make sure that you get the right answer just by plugging it in that way. Again, since we have a base 10 log, we're going to exponentiate with the base of 10. So if I raise everything with a base of 10, that means that log of age hat is equal to 10 to the negative 0.979 power, zero. Sorry, I messed up a few times on this one. 0.0979. So if you calculated that differently, I fixed it. So 10 to the negative 0.979 power gives us an age of about 0.798. And again, I don't know the units, so I'm just writing units. Okay, so we have three types of models. If I'm taking the log of both variables, that tells me it's a power model. If I am taking the log of just the response variable, that tells me it's an exponential model. And if there are no logs, that tells me it's a linear model. For all of them, the ways that I check that a model is appropriate is that the graph of the residuals is a giant scatter, there's no curved pattern, or it has an R-squared value close to 100%. Okay, so those are the ways that I check whether a model is appropriate. And those are the 3 different types of models that we'll be talking about.